Good morning, everybody, and welcome to week 5 of our 15-week webinar preparation course for the Certified Water Specialist exam. Today is September 12th, and we are going to be talking about the ion exchange water process, water softening process. Let's get started. As always, I'd like to say thank you very much. I definitely appreciate the opportunity to serve you, and it is always my goal, any presentation I give or any time I speak with you, to make sure that the information that I give to you is at least as valuable as the time that you're giving to me. I very much appreciate it. Thank you. So what we're going to talk about today, actually, I don't know why we bother this. I don't know what relevance this has to our industry at all. I mean, it's just water softeners and ion exchange and stuff like that. So, you know, la-da-da-da-da. I mean, you guys can pretty much go to sleep on this one. It doesn't really, what relevance is there? But I have an idea. And let's talk about chemistry some more, because 2 weeks of that was, wow, that was so much fun. So let's do it some more. And just a little. It's mostly just going to be review. Okay, we're going to kind of talk about how some of that chemistry stuff ties into the ion exchange process. And then you're going to learn a ton of stuff about water softening, like capacity and different types of equipment and how they work, and countercurrent regeneration and all that stuff. I mean, you know, when I first created this, is obvious I made this slide before I figured out what order I was going to put everything in. So let's just move forward. How about this? What is hardness? Well, hardness is measured chemically by the amount of calcium bicarbonate and magnesium bicarbonate in the water. So when we put our little pink drops in there, or our drops in there, and they turn pink, we're measuring the calcium bicarbonate and magnesium bicarbonate in the water. Yay! So remember last week, you go back in time. Remember, we talked about how water evaporated as part of the hydrologic cycle and went up into the sky and the atmosphere, and it collected carbon dioxide and became a little acidic, and it came down to the earth, and you have calcium carbonate, which is in the ground. That's the CaCO3 that's in the ground. That's the rock, the dissolved rock, until the acid rain dissolves it. And when it's in the water, dissolved in the water, it's calcium bicarbonate. Right, so that's the dissolved hardness, or the dissolved rock in the water. That's also known as temporary hardness. Because I did my, I'm going to give you a little warning this morning. Wow, it rhymes. Warning this morning. I did my certified installer webinar course this morning at between 7 and 8, and I had such a hard time enunciating. I couldn't talk with this. Work anything. I was like fumbling around. I sound like Porky Pig, and so I don't know if that's going to transfer over into this one or not, but we'll see. Could be interesting. So anyway, the calcium bicarbonate that's dissolved hardness, or temporary hardness. So when the water heats up, the carbon dioxide leaves the water and causes the reformation of the rock, or the scale, the calcium carbonate, CaCO3. And it works the same way with the magnesium compound. Hardness due to calcium magnesium bicarbonate is referred to as temporary hardness, and that's because it only stays dissolved for a little while, and then it turns back into its rock, you know, into the hard steel stuff. It happens faster in the hot water because the hot water causes the carbon dioxide to leave faster. Pretty simple. And so it's temporary hardness because that's due to the fact that the bicarbonates will revert back to an insoluble form when the water is heated up. Hardness ranges in this country go anywhere from 1 to 350 grains per gallon. So what is grains per gallon? Well, we in this industry primarily measure hardness within the industry by grains per gallon. The English used grains per gallon way, way, way back when as a standard of weight, and it came from a grain of wheat. So that's where it came. So just to kind of put it in perspective for you, and this is, by the way, a tool that I use in the home. I don't know if those of you on the call or taking this class or in the home doing sales or what some of the reasons are. But when I'm trying to explain it or put it in perspective to somebody, I mean, what does 10 grains mean to somebody? I mean, yada yada, right? But if you figure that 2 aspirin tablets usually weigh about 10 grams. Let me start over. An aspirin tablet, 1 aspirin tablet usually weighs about 5 grains. So 10 grains of hardness is going to be the equivalent of about 2 aspirin tablets. This is, in my test kit, I actually carry a bottle of aspirin with me. And I pull it out, and I'll show it to them. So you calculate, you figure, so let's say somebody's got 10 grains of hardness, 10 grains per gallon of hardness. That's typical city water, a lot of city water. They've got 10 grains of hardness in their water. You figure a shower, even a conservative shower, is going to take, let's say, 20 gallons of water. I mean, if somebody's got a 40-gallon water heater and they got a teenager that runs out that water, 20 gallons is probably a pretty conservative number of gallons used to take a shower. So you've got 10 grains per gallon, then you've got the equivalent of about 40 aspirin tablets worth of hardness running through their water for every shower. So take your hand and pour out 40 aspirin tablets, and because for every gallon of water, you have the equivalent of about 2 aspirin tablets of dissolved rock, worth of dissolved rock going out of that water. So, so that's a pretty big visual. I mean, imagine just for 1 shower, imagine 40 aspirin tablets in your hand of dissolved rock for 1 shower. So that kind of puts it in perspective and explains it to the customer on what that is. Okay. This is a scale. I did upload this picture to the website, so you can get to this. I've had a lot of requests for this because this is one of the common questions: well, how much sodium is added to the water from a water softener? And so this is a chart that came from WQA that tells you your initial water hardness, grains per gallon, and the amount of sodium added per quart of water. And so you can kind of calculate how much sodium gets put in the water. Now, typically the person asking this question is the same one eating their beef jerky and enjoying a can of tomato soup and eating maybe a loaf of bread. Just grab anything. If you want to put it in perspective, anything from their cupboard pretty much is going to have way more sodium than they're ever going to get from drinking softened water. However, if somebody is concerned with sodium in their diet, of course you can use potassium as a regenerate. Or, as always, you can also put in a reverse osmosis system, which takes it all out. The reverse osmosis system is going to be way, way, way less expensive than using potassium chloride as a regenerate. That's the local grocery store where I'm at in Fowlerville. Of course, we have 3 stoplights and a super Walmart. Yay! And a lot of goats, lots of goats. If you're in the market for a goat, Fowlerville is a good place to come. I actually have llamas in my backyard, or emus or something. They all, I don't know, there's some farm animals back there. Anyway, potassium is like $22 a bag at this place. So reverse osmosis system would be way, way less expensive to put in and take the sodium out of the water. Anyway, measurements, it's usually grains per gallon for our industry. Parts per million is more scientific. So that becomes relevant because when you will, if you're out in the field and you're talking to a customer, or if you're following a suggestion that I always have, which is to read and study and know your consumer confidence report that comes from the local municipality, it's going to measure all the hardness. It's going to say hardness as total hardness as CaCO3, and it is going to be measured in parts per million more than likely. So how do you convert parts per million to grains per gallon? Well, it's 17.1 parts per million equals 1 grain per gallon. So if you have 10 grains per gallon, then you're going to have 171 parts per million. So you simply divide the parts per million number that you get by 17.1, and that gives you your grains per gallon. You are going to want to know that conversion. That's going to be important. Okay, so I have a confession. For this page, I just made a screenshot of part of page 70 in the WTF book, and I'm surprised that you guys have not made comments to me about my WTF abbreviations before, so you can insert the juvenile chuckle here. But anyway, I just made a screenshot of it because I didn't want to type the whole thing. Blah, 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 blah. So this just basically is what the last slide said, which is the most common method of designating hardness is grains per gallon. That's in the industry, but everywhere else it's 17.1. Okay. The other relevant thing on this page, just because you are water treatment professionals and you're experts and people are going to ask this maybe, or you can just show off to people and just randomly walk up to them and say it. Hey, did you know water weighs 8.33 pounds? So that's good to know that a gallon of water weighs 8.33 pounds. Okay, so that's good to know. Also, the other thing that's important to know here, or that's relevant to know, is that 1 grain equals 1/7 of a pound. So 7,000 grains is 1 pound of rock, basically. So think about this. Okay, you've got in a water softener. I mean, this also kind of puts it in perspective. Okay, so if you divided, what is 7,000 divided by 5? Just calculate. You too loud. Beat all there. So 7,000 divided by 5. Somebody help me out here with 7,000 divided by 5. We've got. I should know this. I went to Ball State. That's how many aspirin tablets it is. I should actually put that on the slide. That would be good to know. So because that's how many aspirin tablets it would take to make a pound. I can't even find the calculator on my phone. Anyway. Yeah. Anyway, you just divide. Somebody do that calculation if you're interested. Divide 7,000 by 5 for me. 1,400. Okay, thank you. Thanks, Derek. I appreciate that. Wow, that was awkward. So 1,400 aspirin tablets would be 1 pound. That would be 1 pound. That's a lot of. To kind of put it in perspective, if you have a softener that is taking out, say, 7,000 grains a day, it's taking out 1 pound of rock, or the equivalent of 1,400 aspirin tablets. That's pretty big. That's huge. You could, and it's not uncommon to have, 20 grains per gallon of hardness in the water and 4 people in the house. So you get a softener that's taking out close to 7,000 or 8,000 grains a day. That's not uncommon at all. Anyway, so what you're going to see on that water analysis sheet. Thank you. Thanks, Eric, for helping me go through that. I should actually put that somewhere on one of these slides. So if you have a water analysis report and it's showing all the substances in the water, what they're going to do is they're going to give you a total hardness level. So it's going to say hardness as CaCO3 is what you're going to find. But remember, you can have other compounds that make up that hardness. So here, this example shows the calcium bicarbonate is 5 grains, magnesium bicarbonate is 2 grains, magnesium sulfate is 1/2 grain, sodium sulfate is 1/2 grain, sodium chloride is 1 grain, but they're measuring it all as equivalent weights, and so they're giving you a total hardness level of calcium carbonate. So it's equivalent weight. So remember that when you're measuring hardness, it's not just calcium, magnesium that you're measuring. There's a lot of other different compounds in the water that could equal those grains per gallon, that could equal that would make up that hardness. Okay, this is the chart that Jim mentioned earlier that you're going to want to know the chart. I have seen different companies use different charts. This is the one you need to know for the test. You need to memorize this here it goes. You need to memorize this chart. The standard S339, you don't need to know what it's called. You just need to know what you're going to see is a question that says if you have water that is 60 to 120 parts per million or 3.5 to 7 grains per gallon, it is considered blank. And you'll have multiple choice, and you'll have to figure out whether it's soft or slightly hard or moderately hard or hard or very hard. This chart actually, it is an industry standard. The Water Quality Association and the American Society of Agricultural Engineers worked long and hard, get it, hard, on this chart. So show some respect and appreciation when you meet one of the people from WQA or the American Society of Agricultural Engineers. Give them a high five or something. Hey, thanks for that chart, you guys. And they'll look at you and go, well, what chart? This is an industry standard, and you will see something very similar to this in a lot of different places. You'll see it on the EPA's website. You'll see something very similar to it in every dishwasher owner's manual that you have out there. Randomly download a PDF, a dishwasher owner's manual, and in fact, I uploaded one onto the website so you can take a look at it. You can download the PDF and take a look at it. But they'll have 2 or 3 pages usually dedicated to water hardness, and it will very specifically tell you how much dishwashing detergent you're supposed to use based on how hard the water is. And it will be a chart that will be very similar to this. So you are going to need to know this chart, memorize that chart. So the different water softening methods, you can soften by chemical softening, membrane sequestration softening, or cation exchange. The one that we are going to focus on today is cation exchange. That's what we're going to be talking about today. So a little history. You've had water softening that's been around since biblical times. I mean, in Exodus, it talks about it. Here, let me read this verse for you. Exodus 15:25. Okay, there it goes. All right. Then he cried out to the Lord, and the Lord showed him a tree, and he threw it into the waters, and the waters became sweet. Which is, I think I could be on the History Channel, right? On like the Bible, right? Just from my reading, that was pretty good. That was a good Bible reading, don't you guys think? Anyway, so where they came from is cellulose is one of the main components in plants. It facilitates ion exchange. So that's what they think that we're talking about. Hardness removal by chemical softening has been used in industrial and commercial for over 200 years. They added lime to cause the hardness to precipitate. So basically what happens, they have this big reservoir, this huge reservoir, and they would use, they'd add lime, which caused the hardness to precipitate, and then in the 1800s they added soda ash and lime, and that actually removed both the carbonate and the non-carbonate hardness. So that's the way that most municipalities do it even today. You have these big reservoirs, they add lime and soda ash to it, and that causes the hardness to settle down to the bottom of this reservoir. So if you ever looked at one of these big reservoirs, you have this huge layer of thick, nasty sludge. And actually, in a lot of places, they'll reclaim that. Here in Michigan, since we don't believe in paving a lot of our roads, we actually use it on our roads. So because it hardens up the roads, they have to come through and grade them. If you ever come to Michigan, everybody that comes to Michigan always says, why don't you guys pave your roads? I don't know why we don't pave our roads. It's a good question, but we don't for some reason. Anyway, the first cation softener patent was in 19. That question won't be on the test. Why does you won't have a road paving question anywhere near the WQA exam? Nor will you probably need to know any of this history. It's just kind of interesting stuff that came from the book. So the first cation softener patent was in 1908. First one was installed in Moscow in 1910 in an electrical plant. It was a duplex type unit, and we'll talk more about that later. One of the first domestic patents was to somebody named G.R. Shanklin in 1913. So good job, G.R. All right, so here's the components of an ion exchange unit. Now, let me pause for a moment and just simply say that you're going to see some pictures of water softeners and different valves and manufacturers up here on this slide. And I should mention to you that Moti-Vitality nor the Water Quality Association endorses any brand or manufacturer of water softener. Okay, so this all has to say, it's all pretty neutral. So this one right here happens to be a generic picture of a Fleck 5600 valve. Okay, you're going to see some pictures of some other manufacturers here on some of the other slides. If you want your picture, your company or your manufacturer's water softener up there, give me the clip art, give me permission to use it, and as long as it has the features and all that stuff, then I will be happy to use it in my PowerPoint presentation. So just so you know, because I've had people ask me, well, gosh, you got an awful lot of pictures of those other people up there. Do you endorse them? No, I don't. This is all generic stuff. Okay, so the components of an ion exchange unit. First, you got the brine tank. That's where you put the salt in and where you make brine. Then you have the control valve, which is kind of the brains of the beast. That's what controls the regeneration. It's what makes it, actually most of them nowadays are automatic valves. That means they clean on their own, but that's kind of the brain of it. That's what controls the regeneration. The resin column, let me turn on my little pen here. Artwork. Cannot have a Kelly Thompson webinar presentation without some artwork. So this tank is a resin column. I always call it just a softening tank, but apparently the official terminology is resin column. Riser tube. I always call it a distributor tube, but apparently it's called a riser tube. So that's the tube that's in the middle. The brine float. Now, not all water softeners have brine floats. Some of them control the brine using the valve itself. It introduces the brine, makes brine using the valve. But this particular one, and I'd say most of them, have a brine float to them, okay? And the other thing mentioned is, obviously, and some of you guys know this, you've probably seen them, a lot of the box stores have this, but a lot of times you'll take the softener and put it down inside the salt tank. So, but it doesn't change what the components are. Okay, so cation resin. What is cation resin? That's a great question, you guys. Let's answer it. It's a sulfonated polystyrene copolymer cation exchange resin. So, in simple terms, it's basically a plastic polystyrene copolymer that removes positively charged ions. Standard regenerant is sodium chloride, and you can also use calcium chloride to regenerate. You can also use acids. You know, you can use, and in fact, that's part of the DI, the deionization or the demineralization. Remember we talked about chemistry? Everything in that same vertical line on the periodic chart of the elements can be used. They have similar chemical properties. So sodium, potassium, one's right above the other. Well, that's why they can be used. You can also use hydrogen. And remember we talked about acids and bases? The acids have a lot of hydrogen in them, a lot of they're substances that want to release hydrogen ions in solution. Well, those extra hydrogens, they're in the same vertical line in the periodic chart of the elements as sodium and potassium. So you could use that to regenerate a water softener. In fact, they do when it comes to, like I said, deionization or demineralization systems. That's how they regenerate them, is using hydrogen. We'll talk more about that in a little bit. Fully automatic softeners. Like I said, most of the softeners that are out there nowadays are fully automatic. What that means is they go through the entire regeneration process on their own. So they'll have a timer or a clock or something to initiate that regeneration, and it will complete its cycle and run fully automatically. Used to be, and you still see this sometimes on neutralizing filters or on backwashing filters, used to be that you'd have a manual valve on it where you had just a lever and you push that lever up or down to a different stage, and you could manually backwash it. Now everything's done pretty much automatically. Okay? softeners come in 3 different types. You've got your timered systems, and these are the ones that they clean every so many days. So they're set up kind of on these push-pull pins. And if the pin's out, then it cleans that day. So you've got, it'll look like this. And so you'll have these pins around it on the head. And if the pin's in, my drawing is they're a lot more circular and uniform than this. But if the pin's in, then it cleans at night. If it's out, it skips a night, or vice versa, depending on the manufacturer of the valve. So that's the timer system. It's going to clean every so many days, regardless of how much water is used. You're going to set that thing up to clean every 2 or 3 days, or however often. Then you have a demand control, and the demand control measures the amount of water used to determine a regeneration cycle. And then you have the twin tank too, but those are also demand controls. They just control a twin tank. So, but the demand control keeps track of how many gallons are used. So instead of cleaning every so many days, this one cleans every so many gallons. So you would set it up to clean, say, every 800 gallons or every 1,000 gallons. The book says that it accounts for about 2/3 of the units sold today, but this book is over 15 years old. So my guess is that this is going to account for probably 85–90% of the units out there. There are still some timered systems being sold, and you know, there are, on occasion, there is some value in putting in a timered system, but almost all of them that are sold nowadays are the metered systems. They keep track of the gallons. Even the metered valves, you can adjust it to do, you know, if it doesn't clean. The reason a lot of people would put in a timered system is because they want the system to clean every so many days. They don't want it to go 4 weeks in between regeneration. A lot of times the demand controls, most of the demand controls now have a setting where if it hasn't cleaned within a certain amount of days, it will do a light rinse or a light wash, light regeneration. So almost all of them are demand controls, the metered systems nowadays. The demand softeners they tend to be way more salt and water efficient than the timered systems. Some of them actually have resin sensors in them where they'll actually put a wire down in it that measures the conductivity or measures what the capacity of the resin is. And some of them will actually have a modem on that actually dials into the main office and tells you if you need service, and tells them if you need service. It's pretty cool. I mean, if you're into that, I'm not a huge fan of the resin sensors just because the more stuff on there, I mean, it's a great sales tool, the gadgety type thing, and awesome for the people that are willing to stand in line for 10 hours for the new iPhone. But you know, I don't know. That's my opinion. That is not an opinion of the WQA. That's a Kelly Thompson opinion. It's just, but it helps. You know, it's a sales tool. Proportional brining is a good feature. That one is a really good feature that a lot of the softeners have out there. That only it will introduce a brine to the brine tank usually 4 hours before it goes to regeneration, and it will do it based on the capacity that's been used. So if instead of having a float that, you know, a softening tank that has a float in it will put 8 pounds of salt in the softener, or it will make 8 pounds of brine regardless of how much water is used. Okay, so you know, or it will use 8 pounds of salt, not 8 pounds of brine. It will use 8 pounds of salt each time it regenerates, and that's how much, you know, it will use that same amount every time you have a float. Proportional brining says, well, if you've only used 25% of the resin bed, then we only need to make 25% of the normal brine, and that's what they use to regenerate. So that's proportional brining, and that is a good feature that really helps. You're seeing some amazing efficiencies nowadays, incredible efficiencies. So that one does help. Twin tank systems, we'll talk a lot about twin tank systems here in a little bit, so I won't spend a lot of time, but basically they give you continuous soft water in a complete soft water regeneration. So what is salt efficiency? I said I'm talking about being more efficient, and everybody out there, all the marketing brochures, everything always says, hey, ours is more salt efficient than everybody else's. And I mean, you go to 10 different companies and ask them who has the most efficient softener, and they're all going to say, "No, well, we do, of course." But what is salt efficiency, and how do you actually rate it? What's it mean? Well, what that is an efficient softener should be able to regenerate 3,000 to 5,000 grains for every 1 pound of salt used. Okay, so an efficient softener should be able to regenerate 3,000 to 5,000 grains. So let's say you have a 30,000 grain unit. If it were a if you were going to regenerate all 30,000 of those grains of that tank, then it should be able to use 6 pounds of salt if it had a 5,000 grain per pound capacity. Most of them out there most of the softeners out there are right around, even the really efficient ones are right around 4,000, 35, 4,000 grains. Okay, so a 30,000 grain unit would use 8 to 10 pounds of salt to regenerate. There are fine mesh resins or pack beds. You're going to hear the term mesh. Mesh is basically just a size. If you took a jar of marbles, I don't know why you would have a jar of marbles, but let's say you did. Okay, you took a jar and you put marbles in it, and you put the big shooter marbles in it. That would be like a large mesh or a mid-meshed resin. And then if you took the smaller regular marbles and put them in that jar, then you would be able to put a lot more, quantity-wise, you'd be able to put a lot more marbles in that jar. You actually would also have more surface space. Even though they're smaller, you have more surface space because the spaces in between those marbles, these would be horrible marbles to play with because these would be more like rocks. But the spaces in between these are called interstices. Okay, so all these guys right in there, they're called interstices. And so large marbles would have larger interstices in them, and even though you have a bigger marble, because there's a lot more wasted space in between them, you have a less surface area in that tank. So fine mesh or tiny or smaller resin is going to have more capacity per cubic foot. So because it has more surface area. So those are usually a packed bed unit, and they have a higher efficiency. They'll usually give you about a 4,000 grain capacity. The WQA, the book, says that fine mesh units should always be countercurrent. However, I work with a couple manufacturers and a couple clients that use some fine mesh units that are downflow and or downflow brining, and they seem to work okay. So the book says always countercurrent. I don't know if that's absolutely the case, but they typically are countercurrent. And usually they'll have smaller tanks. Usually fine mesh resin units don't need freeboard, and I'll explain to you what freeboard is here in a second, if you don't already know. They typically do need to have pre-filtration because they're going to be more susceptible to sediment and sand and stuff getting in and ruining it. Okay, a little bit more about efficiency. Like I said, 3,000 to 5,000 grains, 3 to 7 pounds of salt per cubic foot, what you typically want to see. A good efficient unit will use 18 to 33 gallons of water, and 3,350 grains per pound is considered to be an efficient unit. So going back to cation resin, these are insoluble plastic beads of polystyrene cross-linked with divinyl benzene. You know, in 15 years of doing this, I've had people ask me what resin is. What is that stuff in there anyway? And being able to say why they're insoluble plastic beads of polystyrene cross-linked with divinyl benzene makes me feel smart, but doesn't mean anything to the customer. What I would recommend you say is, well, they're basically just plastic beads that carry a negative electrical charge to them and attract positively charged stuff in the water. Way more simplistic. But they're usually 0.4 to 1.2 millimeters in size. They contain 45 to 47% moisture, and they remove positive ions. Okay. I'm going to see if you guys can chat. Are you paying attention? here, let's just see where you guys are at here. If cation resin removes positive ions, what electrical charge does it have? What charge does a cation resin have? If it removes positive, good, negative. It has to, right? Because negative attracts positive. It would repel negative ions. Okay, so it attracts. If it's a cation resin, that means that it's removing cations. If it's removing cations, it has to carry a negative electrical charge. The way I always remember this, by the way, is what's an iron filter do? An iron filter removes iron. So if an iron filter removes iron, a cation softener is going to remove cations. And if it's going to remove cations, it has to have a negative charge to it. All right, so let's talk a little bit about salt. So salt's a compound. Remember we talked about that in chemistry? It's salt. And remember we talked about how sodium and chloride love each other because sodium has the 1 electron in its outer orbit and the chloride has a 7 electron in its outer orbit. So they've reached that very stable inert status of having 8 electrons in their outer orbit. Okay? But when you put them in solution, they separate. One goes one direction, the other goes the other direction. Okay? So the sodium carries a positive charge, that's the cation, and the chloride carries a negative charge, that's the anion. So remember, you're leaving here, get out, but you're leaving the TV, right? So that's how they have that's how they became ions, because now the sodium has a positive charge because it left its electron with the chloride. The chloride kept the extra electron, which gives it the negative charge. Okay. So now calcium, magnesium, they also carry a positive charge, but they are bigger and stronger than sodium. So calcium and magnesium is bigger and stronger than sodium. So if you take a resin bead, just one little cation softening resin bead that's fully charged and ready to completely soften the water, it's got a bunch of little sodium ions sitting on it. Now those sodium ions, they're weaker and smaller than the calcium and magnesium, so as the water flows across that resin bed, the bigger, stronger calcium kicks off the smaller, weaker sodium, which then goes into the water, and the calcium magnesium takes its place on the bead. So it's called ion exchange, And that's important, by the way. It's not ion removal. It is ion exchange. Okay? So we're looking at capacity a little bit as we're talking about this. What happens if you have a 5-gallon bucket, and I mean, what's the capacity of that 5-gallon bucket? Well, it's 5 gallons of water. So what happens if you overfill the bucket? Then the water overflows. It starts to run past the bucket. So the resin, same thing with the resin. The resin can only hold so much hardness before it overflows. So you're putting, I mean, just like in the bucket, if you put 6 gallons of water in a 5-gallon bucket, a gallon of it's going to run over. It's going to run over. So if you have a 30,000 grain capacity unit and you put 35,000 grains of hardness through it, it's going to overflow, just like that extra gallon in the bucket of water did. It's going to overflow. So regeneration is emptying the bucket so you can put more water in the bucket. So as the brine flows across the resin, so this is the regeneration process, right? So you're bringing in a huge amount of sodium. And because even though it's weaker and smaller than the calcium, because there's so much of it, it's able to recharge that resin. So basically, this guy right here, the resin bead, he's the mountain. Okay, we're going to play king of the mountain. Okay, and a fully charged resin bead has a bunch of sodium ions sitting on it. So just like that picture right there, sodium sitting on it. Fully charged resin bead has a bunch of sodium sitting on it. So they're hanging out on the mountain. Ooh, this is fun hanging out on this resin. Here comes the big bully sodium, or the big bully calcium magnesium guys. Big bully. We want that mountain. We want to be on it. And they kick the sodium off. The sodium goes into the water, and now the calcium magnesiums are hanging out on that resin bead. Okay? So the sodium there's a whole bunch of them, but they're wimpy. They're these wimpy, small, tiny guys, but they have lots and lots of friends. So they go and they get on the phone and they call all their friends up and they go, we want that mountain back. And so they bring in this whole army of friends. And because there's so many of them, they're able to now kick off that calcium and magnesium, which then goes into the drain and recharge that resin bed. They recharge the resin bead. Okay, so as the brine flows across the resin, the quantity of sodium allows it to force the calcium off. The calcium then goes into the drain. So we got to talk a little bit about co-current versus counter-current. So co-current regeneration is when it regenerates the same exact way as the service. So usually the way it works in service is the water comes in, goes down through the resin bed, and up through the distributor tube, or excuse me, riser tube, and comes out and out through the back of the valve. The regeneration says that regeneration does the same thing. The co-current regeneration flows the same direction as service flow. What countercurrent does, countercurrent goes in through the valve and down through the distributor tube and up through the resin. Now this is really important. Countercurrent is definitely a better way of doing it, no question about it. It's way better, and here's why. Okay, let me just erase these. This really is a great feature. And by the way, the cheaper softeners that you have, the less expensive softeners, if you have a unit that has countercurrent regeneration, you're going to be able to explain this. I mean, definitely the less expensive softeners out there are co-current because the valving for countercurrent is going to be more complicated. Okay, but this area of the resin in this thing only fills up to about here. The rest of this area, all this area, whether it's in a filter or a softener or whatever, is called freeboard. I always think of Leonard Skinner, freeboard! You know, so I could break in the song. If I leave here tomorrow. Okay, let's not. Let's keep talking about water softening. I probably didn't sound anything like Skinner at all there, so I'm sorry if I ruined that for you. But what I probably did do is get that song stuck in your brain now. So anyway, freeboard. So this area all up in here, this is all fresh water. Okay. So if you're cleaning countercurrently, this is why a water softener with countercurrent regeneration is so much more efficient. If you're cleaning co-currently, rather, so you're bringing this brine, you make the brine down here. Let's say you've used 8 pounds of salt and you've got a fully saturated brine solution, and you suck that in through the brine valve, and it brings that brine in. And if you're cleaning co-currently, then you have to have it be enough brine to saturate this fresh water with salt before it ever gets to the top of that resin bed. So not only do you have to make an excess brine, you have to make more brine because this water in this freeboard area is going to dilute that brine solution before it ever gets to the resin bed. So it takes way more salt, significant amount of more salt to clean co-currently because you have to dilute this freeboard area before it ever gets there. What countercurrent regeneration does, it brings that brine solution in, goes down through the distributor tube, and the brine hits the resin before it ever gets to this freshwater freeboard area here. So definitely a significantly lower amount of salt used with countercurrent regeneration than with co-current. The other thing that countercurrent regeneration does is it lifts that bed up. So instead of packing it or pressing it down, it lifts the bed. Now you can get channeling also with co-current. So what channeling is if this is the tube down the center, the riser tube or distributor tube, then, and let's say here's the top of the resin bed, right? And so the tube comes up through there. Water, if you're cleaning countercurrently, or co-currently rather, then the water can come down here, and you might form these little anthill looking things, like streams. So the water may form a path that comes through these little channels here. It's not always going to do this, but it can, and which means that you clean the resin through here, but not necessarily as well through here or through here. With countercurrent regeneration, because you're lifting that bed and mixing that bed up, you're actually able to clean that entire resin bed with a lot less salt. So countercurrent regeneration is definitely a better way of doing it. That all being said, there are some systems out there that work you got to weigh the cost, right? I mean, if you just have calcium in the water, these things are going to work fine. The co-current ones are going to work fine. They're usually going to be less expensive, but definitely the countercurrent regeneration is a good feature to have on a water conditioner. This is a water right softener. It's an evolved system, very good softener, and they were kind enough to let me use the graphics on this. And so this is the service position. So you'll see the downflow, see the freeboard area up here, okay, and the water's going down through the distributor or through the resin, and then up through the distributor tube and out. So, and then that's the service position. That's where it's supplying soft water to the house. Now this is the backwash from the regeneration cycle. You'll notice water's flowing down through the distributor tube and up through the resin. See how it's lifting that bed up and taking up area in that freeboard area, but it's hitting the bottom of that resin bed first. Okay. All right. This is also a Kinetico. It's a twin tank unit. We're going to talk about twin tanks here in a little bit, but you'll see the same thing. The thing with the twin tank I will mention to you is, okay, while this tank is supplying soft, here, let me pause this for a second. The thing with the twin tank unit is you have continuous soft water. You don't have to have a clock on it. There's no clock necessary on a twin tank unit because it can clean in any time. It does not have to wait till the middle of the night to clean. So while this tank is supplying soft water to the home, this one's on standby. When this tank runs out of capacity, it's automatically going to switch over to this tank, to the standby tank, and begin cleaning this tank. Okay, so if you look here, the hard water coming in, the red water coming in, is going down through. When it's softening, it's going down through the resin. Go back over here. All right, so see how this system is being used up. So the red water is coming down. It's using the capacity of that resin up, and the soft water is going out through the distributor tube into the house. Okay, when it switches over to regenerate, you'll notice that it switches, the soft water goes down through the distributor tube and up through the resin. The other thing with the twin tank system, although single tank systems, most of the better quality single tank systems out there will do this as well. They'll fill the brine tank up after the regeneration process. So you're filling the brine tank up with soft water, but with any single tank system, the final rinse has got to be done with hard water. So you lose some of its capacity during the regeneration process because you have to regenerate partially with hard water. With the twin tank system, you can use the entire regeneration process can be done in softened water. That's also a really, really good thing to be able to regenerate the entire system with soft water. Think about this. If you're regenerating with hard water, my King of the Hill example, so remember the sodium, they called up all their sodium friends to come in and kick off the calcium and iron off that resin bead. Well, if you're regenerating with hard water, then in with the sodium, you've got a bunch of calcium and iron spies, right? And so the sodium not only has to fight against the calcium and iron that's on the resin bead, but also the calcium and iron that's in the water that it came in with. So it takes even more sodium when you're with a single tank softener to clean in hard water. It takes even more sodium. So definitely a twin tank system, any twin tank system, is going to be way more efficient than it's going to work. It's going to be more efficient than a single tank softener. I can't say way more because there's some of the single tank softeners out there now when you get things like proportional brining and dry brine tank and countercurrent regeneration. I mean, they're matching the efficiencies of some of the twin tank systems out there, but definitely in terms of cleaning in soft water, that's an absolute better way of doing it, cleaning in soft water. So going back to capacity, just like a bucket can hold can only hold so much water. A resin bead can only hold so much hardness. So the amount of hardness a bunch of beads in a tank can hold is called capacity. So like I said, the capacity of a bucket, of a 5-gallon bucket, would be 5 gallons. Capacity of a 30,000 grain unit is 30,000 grains. And don't get that confused. That's 30,000 grains of hardness, right? So 1 grain per gallon. So if you have 1 grain per gallon of hardness in your water, then you would be able to run 30,000 grains or 30,000 gallons through that softener if it's a 30,000 grain unit, theoretically, right? So the capacity of a water conditioner depends on how many resin beads are in a tank. Brand new polystyrene BVB cation resin has a capacity of about 40,000 grains per cubic foot. Okay, but you never get that again. After the first use, even the most efficient regeneration is not going to bring it back to that level. So generally speaking, this is an industry standard. 1 cubic foot of resin will usually give you 30,000 grains of capacity. And we'll talk about that in a second. So if there is no more room on the resin for hardness or iron, the cations are going to pass through the softener into the home, just like if you tried to put 6 gallons in a 5-gallon bucket. So it's common to have some leakage with any co-current unit, co-current being the way it cleans. Counter-current unit, less likely to have that hardness bleed through or that hardness leakage. The deeper the bed, the less likely there will be to be hard water bleed through. Counter-current regenerated units are less likely to have bleed through, but regardless, a 24-inch of bed depth is recommended unless you have a really high hardness, then a 36-inch bed depth is preferred. So the amount of resin in a tank depends on how big the tank is. Some common tank sizes out there are 8 by 48, 10 by 48, 10 by 54. You can usually these are pretty standardized. So you can usually get a pretty good idea, a rough estimate of approximately how much resin is in a tank based on how big the tank is, based on how big the size is. Now, like I said, 1 cubic foot of resin can remove approximately 30,000 grains of hardness. Okay? So if you have an 8 by 48 tank or a 24,000 grain unit, it probably means it has 3/4 cube of resin in it. 3/4 cubes of 0.75 cubic foot of resin. That's kind of important. Now here's something that I just want to mention to you as well. Do you ever see the movie There's Something About Mary? Whether you did or not, there's a scene where he picks up a hitchhiker and the guy is he's crazy. The guy's nuts. And Ben Stiller is driving down to the south, and he picked up this hitchhiker, and the guy's like, I got this business idea, and you heard about 7-minute abs, right? Well, I'm going to do, or the thing is 8-minute abs. He goes, you heard about 8-minute abs, right? I'm going to do 7-minute abs, right? And so if somebody says that somebody is at the video store and they see 8-minute abs and they see 7-minute abs, then they're going to always pick the 7-minute abs because that's going to be the one. They want 7-minute abs. And then someone says, yeah, but then somebody else is going to do 6-minute abs. The guy's like, no, man, you're not getting it. But anyway, you should watch the movie. It's a very funny movie, and I like it. So, and I probably got the quote totally wrong. But my point is that when you go to the store and different, you're shopping for softeners, or you have your competitors out there and they say, well, ours is a 32,000 grain unit. And then the other guy says, well, ours is a 33,500 grain unit. And then the other one says, well, ours is 36,000 grain unit. Well, they may actually put a tiny little bit more of resin in there, but the reality is it's probably a cubic foot. I mean, you go by the industry standards here. It's probably just marketing, because you can, if you salt it right and set it up and the proper efficiencies and everything, you can get 35,000 grains out of a cubic foot of resin. So, but in reality, in real life, when you're installing it in the home, that's not the way they're set up. And in fact, it gets even worse than that. There's something called reserve capacity that nobody ever talks about, because you got to have reserve. The book, WQA book, doesn't even talk about reserve capacity, but every manufacturer out there does it. Some have used that are in sales, you may not figure or know how to figure reserve capacity or the capacity of a unit. You're about to. I'm about to show you how to do it. But the truth is, even the question that you have on the WQA quiz is going to ask you to calculate capacity, and they don't even take into consideration reserve capacity. So just a hint, when you get a question about capacity on the quiz or on the test, do not use reserve capacity. However, in real life, you got to figure reserve capacity. And I'll explain to you what that is here in a second. And by the way, I am helping WQA rewrite their certification program, and we are adding in questions on it. We are calculating reserve capacity because an industry standard says that you only use 2/3 of the capacity of the tank. You got to save 1/3 for reserve capacity. So we'll get to that in just a second. So capacity, a 30,000 grain capacity unit can theoretically remove 30,000 grains of hardness. That means if you have 30 grains per gallon of hardness, the system could soften 1,000 gallons of water. Okay. Now for some people, I've done this enough with people, even training them in person, where for some reason the math on this stuff gets really hard for them. So if you get lost on this, guys, call me. Okay? I'll work it out with you. I'll help you figure it out. I'll walk you through it, but don't overcomplicate it. Don't overthink it. This is really pretty simple. If you have just like the 5-gallon bucket, what's the capacity of a 5-gallon bucket? It's 5 gallons. So if you have a 30,000 grain capacity unit, the capacity is 30,000 grains. Okay, so if you have 30 grains, you can soften 1,000 gallons of water. It's grains per gallon, grains per gallon. So reserve capacity. The system, since a single tank softener has to wait till the middle of the night to clean, then when you size up the system, the industry standard says to use 2/3 of the tank capacity, leaving a 1/3 for just-in-case scenario. So let's say, for example, that the system, it's a metered system, keeps track of the gallons, and it knows it needs to clean. Let's say that, okay, so a tank can remove 30,000 grains of hardness. You'd size it up as if it were a 20,000 grain system. Okay, so if there's 30,000 grains of hardness in the water, 30,000 grains of hardness, in the system would clean every 667 gallons instead of every 1,000. Okay, so this is a metered system. Let me just explain this to you. So you got a metered system. If you did not put the reserve capacity in there, the meter knows that it needs to clean every 1,000 gallons. That's because the system can remove 30,000 grains, which means that it needs to clean every 1,000 gallons. So Friday night it checks itself, and it's only cleaned 900 gallons. It's only cleaned 900 gallons. So the meter says, well, I'm not at 1,000 gallons yet. I can go a whole other day, or I don't have to clean yet. Okay. So the next day comes along, and you have company, and it's Saturday, so you're doing laundry, and the kids are home from college, and everybody's showering, and you're using a lot of water, and by 10 o'clock in the morning, you used up that 100 gallons of capacity. Since the system has to wait until 2 o'clock in the morning to clean itself, you're going to go an entire day with hard water bleed through, putting that extra gallon in that 5-gallon bucket, that 6 gallon. That you're going to get hard water bleed through, which means you're going to fill up your water heater, you're going to get staining if you have iron in the water, all of that. So what you do when you set up a single tank system is you have a reserve capacity. You put in a just-in-case scenario, and usually industry standard says that that's going to be 1/3 of the capacity. So in this case, you would leave 333 gallons for the just-in-case scenario to get them enough water to get through an entire day. Okay, enough water to get through an entire day. Now this is also where it comes into efficiencies. If you've got a metered system, just a typical standard metered system with a float in it, with a brine float, if you've got a float in your brine tank, then you've got to make enough brine to clean that entire resin bed, including the reserve capacity. So you're using, every time it regenerates, you're using enough salt to clean the entire capacity of that resin bed, regardless of whether it's used it or not. This is where proportional brining and having a dry brine tank comes in handy. This is a nice feature. It's a really nice feature. Salt tips: use a good quality salt, regenerate more often, use a sediment filter, follow recommended backwashing instructions, use resin cleaners when appropriate, so if you have a lot of iron in the water, and be aware of what's in the water. Things like oxidizing agents like chlorine will basically turn the resin to mush. It's going to destroy the resin. So you got to take chlorine out. If you have a water softener on city water with chlorine in it, then you need to take the chlorine out because it'll destroy the resin. And then other cations like barium. So just like you can use sodium and potassium to regenerate the softener, well, things like barium will the ion exchange will take up the room. They'll take up the capacity. So if you're getting hard water bleed through, it could be that you have other cations in water that's taking up space that could otherwise be used for the calcium magnesium. A full strength brining, contrary to what some people think, this will not harm the resin bed. It will not harm the resin bed. In fact, it's actually good for it. It shrinks and dehydrates the bed, so it's good for mixed bed units, especially like tannin. If you're putting tannin resin, which is an anion resin, and cation mixed together, then it's good for it. It's also bacteriostatic. A full-strength brining is bacteriostatic. It will kill the bacteria in the water. 26% brine or salt is considered a full-strength brine. So 26% brine. If it's brought in by an eductor, then it's usually diluted 10 to 12%. You get a higher with countercurrent regeneration. You get a higher regeneration percent or a higher percentage of brine with countercurrent regeneration than you do with co-current because of that freeboard area, that freshwater freeboard area there. But a full strength brining is definitely going to be best for fine mesh units or like I said, fine mesh units. Okay, so duplex or paraflow insulation. This is where higher flow rates are needed. So when you look at this guy, let me put my little drawing pin in again. So these guys are probably installed in duplex for parallel. Now some people call these, there's one manufacturer that calls it overdrive. You may have a different name for it. There may be different names for it, but paraflow or duplex, they're all the same thing, okay? So basically the reason you would do this is much the same way you would install filters in parallel, is for higher flow rates. So you see both of these systems here, both these softeners. Water's flowing through both these guys at the same time, okay? That gives higher flow rates. Now, they have to regenerate. Keep in mind that when they regenerate, still a good idea to have them regenerate in the middle of the night because let's say that you're putting these in and you need a house has multiple shower heads. Okay, the big high flow shower heads in their bathroom, they have multiple shower heads, and let's say they need 21 gallons a minute of flow. That's pretty common of water. So most of your softeners, your residential softeners out there will give you surface flow rates. Now, through the valve, you can get a heck of a lot more water through a valve, but you add resin to it, and now you're restricting the flow of the water. So most of them, even the high flow ones, are going to give you 12 to 14 gallons a minute, which is plenty for most people. But if you've got these high flow faucets that require 21, 22 gallons a minute to run, then you need more. You can't restrict the flow like that. So you can install these things in parallel. You put them together, so now you're basically doubling the amount of flow that you can get through them, which gives you plenty of water. Keep in mind, if it's regenerating in the middle of the day, if you've got it set up to regenerate in the middle of the day, then during its one regeneration, you're going to be down to that 12 or 14 gallons a minute flow through that one softener. So usually these will still regenerate in the middle of the night, but they'll stagger the regeneration. So this one will go, say, at midnight, and this one will go at 3 o'clock. Okay, so they'll stagger the regeneration. You'll see this a lot in commercial settings. So look at these 1, 2, 3, these huge softening tanks they have down here. Here, they can't afford probably to ever have a reduction in water pressure like I was talking about being down. So two of these softeners will probably supply the water pressure the factory needs, or whatever commercial place this is, will probably supply enough water pressure so that you always have, they'll stagger the regeneration on 1, 2, or 3 for different times so that it can go whenever it needs to. But the water is going to run through all 3 of these tanks at the same time. And this could be a car wash, actually. I just had, about 6 months ago, I had an opportunity to help somebody with a car wash unit, and it was very similar to this, looked very similar. One thing with duplex or paraflow installation is it also will give you 24-hour soft water. You'll have 24-hour soft water with it. So continuous soft water, very nice. Maybe multiple units. I've been in restaurants before where I've seen 6 or 8 of regular softeners hooked up because they're blowing through so much water for dishwashing and stuff like that. So they're putting, you know, just a whole line of softening tanks in that have different regeneration times. Twin tanks, like I mentioned earlier, I already talked about these a little bit, but they do give you 24-hour soft water, continuous soft water. The entire regeneration is done in soft water. That's kind of a nice feature. There's no clock necessary on them, although some of them do still have clocks on the computer, but there's no clock required for the regeneration, not typically. And they're installed based on water chemistry, not the number of people in the home. So that's kind of nice too. So they're installed based on water chemistry, not the number of people in home. And that means that you don't need the same reserve capacity. Now, some of them still do set up a little bit of a reserve capacity, but most of them, I mean, you don't need the reserve capacity because it can clean whenever it needs to. Whenever it can switch over and clean as soon as it needs to. You may have some issues if the water pressure is low. So we have some clients out east, for example, that have little jet pumps. Actually, we have a client that works a lot with the Amish, and they have generators and jet pumps that supply water from their well. It always is interesting to me that they have generators, but that's okay. But anyway, they don't pump in a lot of water. So if you have a twin tank system that, say you've got a jet pump and half-inch plumbing running through the house, which happens sometimes, and the system goes to clean in the middle of the day when you're trying to do laundry or take a shower or use water, then you could have some pressure issues because it's just one more water-using appliance using up that water. That's not always the case. Most of the houses out there that have a standard well, I mean, you should not ever notice a reduction in the softener. Not if it's sized properly and you've got the right softener going, but it can be an issue, so it's something to take into consideration. One of the clients that we have has a cool feature on their system. It's kind of a unique feature. It's a twin tank system, but you have a valve on each tank, but this valve here is a secondary valve, and basically what it does is it waits until it waits to complete the regeneration of the standby tank until right before it switches over. And the reason I think this is kind of cool is this is a limitation to the system that I have. I have a twin tank softener in my house, and I travel a lot of times every other week. There are times that I'm gone every other week, so I'm not even at home. And when I am home, it's just me and my 2 kids. So so my softener only regenerates sometimes once every 2.5 weeks. If it was set up the way it needs to be, the way it could be set up, would only regenerate every 2 or every 2.5 weeks. That's a problem because it regenerates when it switches over tank. It switches over to the secondary tank and immediately goes through its regeneration. So that means that I've got water sitting in standby tank for 2 weeks or more sometimes. So sometimes I get a little odor to my water. Sometimes I get a little iron bleed through because it comes through there. So I have to set my system up because it's totally based on water usage. I have to set it up to clean more often than it needs to, or sometimes I go down and manually regenerate it when I get back from traveling. And So I end up using more water and more salt than I need to. So it's kind of a limitation. That's why I kind of like this feature on this unit, because it waits to complete the regeneration standby tank until about 4 hours before it's going to switch over. So it's kind of a neat feature. Keeps water from being stagnant or iron staining from coming to it. So benefits of soft water, really, if you guys have been doing this job for more than 2 days, you probably know this. I mean, seriously, if you're listening to this course, you probably already know it. But cleaner skin, appliances last way longer, razors last longer, cleaner dishes, guests don't complain when they visit, mother-in-laws don't complain as much. What do they say the difference between in-laws and outlaws is? That outlaws are wanted. Anyway, moving on. Soft water and domestic water heating. Scale forms way faster in hot water. Remember, we went back and we talked about that because it causes the water to expand, and the carbon dioxide leaves the water faster, and therefore the calcium bicarbonate forms faster, right? Or the calcium carbonate, the CaCO3. It forms way faster in hot water. Here's something interesting. Hard water scale has a 5% thermal conductivity, and that's about the same amount as fire brick. So imagine this. I mean, you talk about saving efficiencies here. If you took a pot of water and you put it on a gas stove, gas or electric, and you wanted to boil that water. Now you timed the amount of time, you turn the gas on high and the flame on high, and you time it to see how long it's going to take to boil that water just with the pan sitting directly on the burner. Okay, that's great. Now you time that. Now take an 1/8 of an inch piece of calcium and a calcium carbonate, calcium, a rock, and you layer it, you put it down in between that burner and that pan. And now you light that fire and see how much gas it takes, measure how much time and how much gas it takes to boil that water. It's going to take a heck of a lot more energy to heat that water up and to boil that water than it did without that rock there. Well, that's the same thing that happens when you have scale buildup on the heating element in the water heater. You've got to heat that rock up first before you can get to the water. And so obviously it's going to take a lot more energy to heat the water through that fire brick, essentially, than it does without it. The New Mexico State University did a study that said that having a softener will save 22% of energy on soft water. Even beyond that, if you go look at the Battelle study that WQA did a couple years ago, or they sanctioned a couple years ago, you're going to see a lot more statistics than that. So it's the Battelle study. Contact WQA for that. It's an awesome tool to have. This is just a personal little thing. WQA doesn't suggest this necessarily, or and you're not going to find this anywhere in the books or on the test or anything, but my suggestion, I just think for professionalism, the water heater should be drained. I believe that if somebody's spending a couple $1,000s on a water softener, they want the benefits of that pretty much right away. Now, I understand that some companies don't like to do that. They don't like to touch I mean, draining is pretty easy. You just hook a hose up down to the water bit that comes out of the side of the water heater and drain it out. Otherwise, what's going to happen is it's going to take them 3 or 4 days before they get the benefits of soft water, because it's a storage tank, essentially. So you need to, I mean, I know that some companies don't like to do that because they open up that hose bib, and if you have debris or sediment or crap in the bottom of that water heater, then it can clog keep the hose bib from closing back up, and it can leak, and there can be trouble with it. So if you are hesitant about draining the water heater, then at least tell the customer, at least explain it to the customer, or explain how to do it, or have them sign off on it or something. Just at least make them aware that of what's going on with the hot water, so that they understand that they're going to have hardness in there for a couple days. Okay. Reverse osmosis and soft water, it's best if there's no hard water bleed through, so a duplex or a twin tank system is recommended. Most reverse osmosis systems out there will tell you no more than 3 grains should be allowed into the RO. The RO membranes are going to foul a lot faster with hard water. Softening and iron removal by cation exchange. Iron stains at 0.3 parts per million. Manganese stains at 0.05 parts per million. Dissolved iron only, so ferrous iron only, and we're going to talk more about iron and manganese and hydrogen sulfide coming up in a couple weeks. But this will only take out ferrous iron or clear water iron. It will not take out ferric iron. Some of the rules: eliminate any contact with air or oxidants, so bleach or chlorine or any oxidants, because it will oxidize it and keep it from removing the hardness. Regenerate the softener vigorously and often before actual softening capacity exhaustion. Stay under 5 parts per million. Some manufacturers say 15 parts per million, but and I've actually done it. I've installed softeners on really high levels. As long as it's clear water iron, it will take it out, but you got to salt the heck out of it. Okay, it's best if the pH is slightly acidic, and you need to put a bunch of salt the heck out of it. Okay, so regenerate the softener vigorously and often before the actual softening capacity exhaustion. Should have 2 grains of hardness for every 1 part per million of iron to prevent the resin fouling. At least 2 grains of hardness. And that becomes an issue if you have low pH water. A lot of times it's naturally soft water also. And so if you have a lot of iron, then you need to add hardness back to it through a neutralizing filter like the calcite filter. And that's going to be, that will help take out the iron. A few more rules: use downflow softening, but it's best if you can use upflow brining or countercurrent regeneration. Use high backwashing rates with 100% bed expansion and turbulent agitation. Best if there's 7 grains per minute per cubic foot. Right. Warmer water is better, at least 50 degrees Fahrenheit. Use at least 10 pounds per cubic foot if you have iron in the water. And use a complete soft water regeneration if you're able to. So a soft water regeneration, definitely better when you have iron and manganese in the water. Use a resin cleaner periodically. What the resin cleaner does is, as the iron converts from clear water iron to oxidized iron, which is going to do some. So, okay, so a resin bead basically has all these little holes in it. So they're not just these solid round little beads. They're like Swiss cheese. They have all these little channels and holes. So the surface area is not only just on the outside. You have all these little holes and these tunnels and everything all the way through that resin. So, I mean, they're tiny at the molecular level. So ferrous iron, clear water iron, is really itty-bitty. It's at the molecular level. It can get in and kind of move in and out of those caverns. But if it oxidizes at all or converts to ferric iron at all, then it can clog those holes. Okay? It can clog that. So what resin cleaners do is they go in and they redissolve the iron and convert it back to ferrous iron so that it can be backwashed off. So they clean out those holes in the resin. So resin, cation resin, will not remove oxidized bacterial or colloidal iron. Just a word on something called compensated hardness. Since iron is more difficult to remove than hardness, industry standard, or at least the WQA's recommendations, and I say WQA's recommendations because I've worked with clients all over the country. Different manufacturers have different rules, and obviously when you're out there working with your company, you need to follow the rules that your company recommends. Okay? But Water Quality Association says that compensated hardness should be calculated by taking the actual hardness and multiplying, and then taking the iron, multiplying the iron by 3, and adding that to your hardness. Okay, so if your hardness is, say, 20, okay, and your iron is 2, then you would multiply that by 3, okay, equals 6. So your compensated hardness in this is going to be 26. Okay? So your compensated hardness is going to be 26 in this case. Heavy metal reduction. water softeners will remove certain cation resin, will remove certain heavy metals like cadmium, copper, zinc, lead. They're usually going to be in a cationic form. If you have these things in the water, then you need to salt the heck out of them and check for their presence often because they're not good for you in the water. Barium occurs naturally. It is on the EPA's maximum contaminant levels, and its maximum contaminant level is 2 parts per million. It acts just like calcium and magnesium, works the same way. Okay, deionization, last thing we're going to talk about. We are going to talk next week about the anion exchange. We're going to talk more about ion exchange, but we're going to focus on the anion side of it. But with deionization, an introduction to deionization, another word, by the way, is demineralization. Deionization or demineralization, they mean the same thing. The terms demineralization and deionization mean the same thing, but deionization is actually more accurate, okay? So what happens is a two-step process. First, the waters run through a cation resin bed that takes out all the cations. But instead of the resin being regenerated with sodium, it's regenerated with hydrogen. Remember the periodic chart of the elements? Okay, hydrogen in that same vertical line as sodium and potassium, so you can regenerate with hydrogen. So the first step is the resin, instead of being regenerated with sodium, it's regenerated with hydrogen. So what comes out of the first step is water. It has a bunch of hydrogen in it, which, by the way, is going to make it very, very, very acidic because, remember, the more hydrogen, more free hydrogens in a solution, the more acidic it is. So what comes out of the first step is water that has a bunch of hydrogen in it, as well as all of the anions left in the water, or the negatively charged ions. In the next step, second step, the water with the hydrogen and all of the anions in it run through an anion resin. An anion resin is going to take out all the positively charged ions. Okay? So, I'm sorry, it's going to take out all the negatively charged ions. So that removes all the negatively charged ions, but it doesn't mess with the hydrogen, as that's a cation. You regenerate the anion resin with hydroxide, which, if you recall from last week, is Mickey with a severed ear. So the result, what's left after both steps, is water that has a positively charged hydrogen and negatively charged hydroxide ions in them, which then form each other to make H2O, so deionized water. Yay. Okay. So, municipal systems put lime soda ash. It's commonly used in municipal water treatment systems. It causes temporary hardness to precipitate out of the water. It doesn't make the water completely soft, but it usually take it down to 5 to 10 grains. It's not really feasible for residential treatment. And that is all for today. I would like to let everybody know that we are filling up our schedule for our fourth quarter. We have availability. We can hire, we can train, we can work with your team, help them create business. We do far more than just WQA stuff. We work very specifically with the water treatment industry. So if there's anything we can do, please let me know. Everybody else, thank you very much. Have a great weekend. I will talk to you next week. We're going to talk more about ion exchange, and we'll talk to you soon.